Today, April 22nd, represents Earth Day around the world, and there's no better way for us here in Mission Control to celebrate Earth Day than to have a special guest joining us for the, I guess we can call it a celebration, and that is Dr. William Stefanov. He is the Associate Space Station Program Scientist for Earth Observations. You're also the lead for Earth Science and Remote Sensing Unit here at the Johnson Space Center. Welcome, Will.
Thanks, Kyle.
It's good to have you here. We know that for years and years, one of the tasks that the crew loves to do is look out the window, but it's a lot more important to that for the team here on the ground. But why is it so valuable to look at the Earth from the ground?
Well, it's part of a long-standing tradition of looking at our planet from space. The perspective from orbit allows us to see things that you can't really see from the ground. It also allows you to collect data that our eyes necessarily can't recognize by looking at different wavelength regions. And also it enables us to collect data over remote parts of the Earth on a very regular basis that might be impossible or difficult to get out on the ground to actually take specific samples or specimens or measurements of.
Right. So talk a little bit about the different kinds of cameras. We see Earth views all the time, obviously, but talk to us about the different kind of cameras, the sensors that are aboard the space station right now that are pointed down or looking at us here on the Earth.
Okay. Right now, I'm going to focus on the NASA sensors, although our international partners also have their own systems on board. Well, I'll start on the exterior of the station. What you're looking at right now is the Japanese experiment module and its exposed facility. And if you follow the Canadian arm at the bottom of the image out to its end, and then look pretty much straight up towards the top of the photo, you see a white box that looks like its front is cut out.
Right.
And there's a sort of a mylar-wrapped instrument package in there. Inside that instrument package sits the HICO, the hyperspectral imager for the coastal ocean. And that is a sensor that is specifically tasked, as its name suggests, on looking at oceanic processes along the coasts. It's a hyperspectral sensor, which means it looks at a large portion of the electromagnetic spectrum, broader than our own eyes can see, but it chops that spectrum up into 128 different little slices. And by looking at the energy that returns back to the sensor from the Earth's surface in each of those little slices, you can actually build image spectra. These can be thought of as fingerprints, if you will, for specific chemicals or materials on the Earth's surface. So some of the things that they've used that sensor for are, the EPA in particular has looked at water clarity and water quality, for one thing. And they've been developing apps that people can use to see what the water quality is at a particular spot that they might be, say, wanting to go to swim in or so. Now we're going to move inside the space station because we have sensors both exterior and interior. Here you see a picture of former ISS commander Chris Hadfield, and floating there in front of him is the I-SERV camera system. And this is the I-SERV Environmental and Research Visualization System. It was specifically built to support the NASA SERVIR program, which collects data and helps developing countries develop things like maps of agriculture, respond to disasters, and things of that nature. This is the I-SERV camera system mounted in the wharf, which is the Window Observational Research Facility. This is inside the U.S. Destiny Lab module, and it's specifically designed for remote sensing instruments to be positioned inside and look through the Destiny Lab window.
And that's a very polished window compared to other windows on the station, right? Specifically for this type of observation.
Exactly. In fact, it's the finest optical quality window that's ever been sent up on a manned spacecraft. And what the I-SERV system is, it's kind of an innovative design. It's a high-end commercial off-the-shelf digital camera mated to a Cassegrain astronomer's telescope, very similar to what an amateur astronomer might buy at home. And putting those two together allows this camera system to collect very, very high-resolution data on the Earth's surface, about 3 meters per pixel. Still inside, the other sensor system that we have is the Crew Earth Observations Facility, and this is the kind of data that's been collected for the longest time period on space station. Astronaut photos taken with handheld digital cameras out the station windows has been collected since 2000. And here you see NASA astronaut Don Pettit in the cupola. And he actually has a dual camera system that he rigged up where he's taking infrared data with one camera and visible wavelength data with the other camera. And so all these systems put together enable the ISS to collect a wide variety of data for a number of different surface processes. We're also going to have, actually going up this year, being installed this year, 2 new sensors, the CAT system, the Cloud Aerosol Transport System, and the ISS Rapid Scat system. And what CATS will do, it's an atmospheric sensor, and what it does is uses a laser system to look at aerosol concentrations in the Earth's atmosphere, and that relates directly to climate change investigations. It provides data useful for determining how much energy is absorbed by the atmosphere and reflected back into space. The Rapid Scat system looks at the sea surface, looks at wind patterns on the sea surface, and that also gets back to looking at how, in a warming global climate, how surface circulation patterns change.
Well, now you've talked a little bit about some of the instrumentation on the station, but let's talk now about, maybe show us or talk to us about some examples of what we've learned thanks to some of those instruments on the station.
Okay. This slide, what you're seeing right now, this is a HICO scene of Galveston Bay. And unfortunately, JSC is just off the edge of the image there. We're not quite there yet, but the greater Galveston Bay system. And like I mentioned earlier, this kind of data is being used by groups like the EPA, also other groups, particularly a group that I lead here at JSC, looking at regional climate change and hazard and potential sustainability issues for the center itself. This is a hyperspectral sensor, but right now you're looking at a visible camera, sort of a visible wavelength view. Right. So it's more intuitive to our eyes. But if you go into that, each pixel on that image, you can pull out spectra that's useful for looking at things like I said, water turbidity or presence of algae, certain bacteria, different chemical constituents in plants, all things that are useful for looking at how climate reacts to different changes.
Right.
This is a image on the right taken by the I-SERV camera system during floods during 2013 that happened up in Calgary, Canada. And what you see on the left is a pre-flood image taken by from the Google Earth software environment, and on the right you have the I-SERV camera system. And this was data collected in response to this hazard event, and the data was sent directly to the Canadian response agencies for use in their mapping of the flooded areas, and it's sending aid to the proper parts of Calgary. And this is actually an activity that all of the NASA ISS sensors, including some of the international partner sensors, are engaged in as part of the International Disaster Charter, where if there's a global natural hazard that takes place, the ISS sensors, if they can collect data that is then given to the people in those countries for their use in their hazard response. And this is a image sequence taken by the Crew Earth Observations Facility, the handheld digital cameras, of the Uppsala Glacier in South America. And what we're seeing is 3 time periods, and what we're looking at is the snout, the end of the glacier, where it goes off into that fjord, into the water, and being able to track how that has moved backwards in time, primarily due to loss of glacial ice due to warming in the region. And these images were all taken at the same season, so we can control that we're not just looking at a seasonal variation. We're actually seeing actual retreat of that glacier over time.
Well, there are obviously other Earth observing spacecraft up there, satellites and such, but are there advantages? Obviously there are, but can you talk a little bit about the advantages that we have with the systems on the station compared to those?
Well, the main advantage right now is in the ISS orbit itself. Most of the traditional remote sensing systems that NASA and other countries have are polar orbiting satellites. So they're designed to cover the whole surface of the Earth at approximately the same time of day, so the sun's illuminating it at the same time. And what this does for most of these satellites, that means you only go over the same spot on the Earth about every 2 weeks or so. That's changing with pointable sensors now and sensor constellations. Right. But that's really good for developing a nice regular time series of data. But if you're interested in taking data at other times of day, where you're looking at things that don't happen to happen at the time the sensor passes over, you can't really get that with these sensors. What the ISS does, because of its inclined equatorial orbit, it has the capability to pass over different spots of the Earth between 52 north and 52 south latitude at different times of day or night. So the sensors on ISS can collect really a fundamentally different kind of data, different data set.
Well, yeah, and I'm sorry, but you've got one more advantage, I guess, and that is you have humans in the loop. You have crew members on board that can help you as well. Can you talk a little, just for a minute, about that?
Sure. Yeah, the ISS is a unique remote sensing platform in that there are humans on it. And so what that gives you the ability to do is serendipity, basically. The crew can look out the window and see something happening and take imagery of it, just decide on the spot to take imagery of it, where all of the automated sensors, the ground commanded sensors, they get a daily set of targets that are uplinked to them, and they collect data whether there's something going on or not. The crew can also look out the window and say, all right, we're taking a shot of this particular image that's flooded, but it's completely cloud covered. We're not going to get any data. So they can decide, well, there's no point in taking that image, whereas the automated sensor will take the data regardless. So it gives you that added human in the loop ability to respond immediately to something that's unfolding.
Well, Will, I appreciate it. We all appreciate you stopping by on this special day, Earth Day 2014.
My pleasure.
And we really appreciate you coming by.
Thank you.